Hello, everyone. I'm Jing from the University of Illinois at Urbana-Champaign. Today, Yihan, Boyuan Tian, Jeffrey Zhang, and I will present our paper, ILLIXR, Enabling End-to-End Extended Reality Research. I want to point out that the student leader of this project is Muhammad Huzaifa. He's sick now, so there are four of us representing him. With the end of Donald scaling and Moore's law, we have entered an era of specialization. The graph here from Professor Brooks and Professor Wei's group shows the number of specialized IP blocks on the Apple processors on several generations of iPhones. We can tell that there's an explosion of accelerators in system on chips. The die photo is one such example. The computer architecture community has done a lot of work designing specialized accelerators. However, our question is, what about a specialized system? To be more precise, how are the accelerators going to communicate with each other? What is the software stack? How do we write applications in the system? A parallel trend is the rise of the edge, with many examples like virtual reality, agricultural robots, autonomous vehicles, etc. The common characteristics among all these edges are the challenging performance demands, the stringent resource constraints, and the end-to-end quality metrics that we need to abide by. These two trends together motivate the need for scalable and generalizable system specialization. For scalability, we mean the end-to-end quality of the system should scale with the resource usage. The number of application features should scale with the hardware-software design time. For generalization, we want generalizable techniques that are application-driven, end-to-end quality-driven, and co-designed in a hardware-software application manner. But the question is, what application should we use? We were frustrated by the toy benchmarks and applications that we had worked with. So we need a realistic application testbed that will enable us to do better and more grounded research. In this paper, we make the case to use extended reality, or XR. Extended reality includes virtual, augmented, and mixed reality. We and many others believe that XR is going to be the next computer interface that has the potential to transform human activities, including science, medicine, education, and more. However, it is challenging to design an XR system. There is an orders of magnitude gap in power, performance, and quality of experience between the current XR headset and the desired one. For example, for a full immersion, we would like about 200 megapixels resolution, but current state of the art delivers about 4. To wear XR glasses all day everywhere, power needs to be in the hundreds of milliwatts range versus the 10-watt range state of the art. And there are similar large gaps in other metrics, which is shown in table 1 in our paper. This is an exciting opportunity for computer architects. XR comes with additional challenges. First, designing an XR system requires diverse expertise, including graphics, vision, audio, video, optics, haptics, and more. Second, to get the performance benefits, we cannot rely on just one layer of the system stack. We will need cross-layer system optimizations where we co-design the hardware, the compiler, the OS, and the wide range of algorithms for a complete XR system. Third, metrics to measure the goodness of an XR system are complex and still a subject of research. XR requires multiple user-driven end-to-end quality of experience metrics such as motion to photon latency, image quality, audio quality, and more. Finally, when we started this work, XR was dominated by a few participants with closed systems. There were no open reference systems or benchmarks to jumpstart for XR research. In other words, there's a large barrier to entry for open R&D in XR. And our question is, how can we democratize XR system research, development, benchmarking, so a broader community can address the challenges and move this field forward? We now present our Elixir system, which enables end-to-end extended reality research. Elixir stands for Illinois Extended Reality Testbed. It is the first open source full system XR testbed for computer architects and system engineers. Elixir has state-of-the-art XR components integrated with a modular runtime. Elixir is extensively characterized and can be used for research on both desktops and embedded systems. Next, I'm going to pass it to Jeffrey.
Hi, everyone. I'll be showing a few demos that demonstrate Elixir in action. So this first demo here is standalone Elixir, and this is what you can run right off the bat when you clone our code. So Elixir is taking in sensor input, so a camera and eye view, and it's producing a iBuffer output. And this is what you would actually see in a headset if that headset was running Elixir. This over here is a debug view, and that's just to help show that tracking is working accurately, as well as having some debug values. So as you can see, when the user in like this camera feed crouches, that motion is accurately reflected by this headset. And when they turn and look around, that's also reflected by the headset. It just shows that tracking is robust and working well. And just to clarify, you don't actually need a headset to run any of this. This can all be run from your desktop computer. In the case that you do have a headset like we have here, you can run Elixir like on a desktop computer and have the output be displayed to like some headset you have. And this headset we're using here is the North Star headset. It's an open source headset. And as you can see, the student who's walking around in the scene, their movement is reflected in Sponza right now. So as they walk forward or look around, you can see how the tracking is working well between the user and the scene. But if you want to take it a step further, like in this demo, we have a backpack computer that's running Elixir. And again, the North Star is just displaying the output of Elixir. And everything you see here is completely open source. Elixir is open source, and the North Star headset is also open source. So if you had all these things, you can run experiments yourself as well. But again, you don't need an actual headset to run Elixir. So Elixir has come a long way, and we've been doing a lot of research with it, and there's still a lot of research to be done, and we can't do that all by ourselves. So we have this Elixir consortium where we have industry and academic partners, and the goal of this consortium is to provide an open source standardized reference for this testbed. So the goals of this consortium are to standardize a set of components and interfaces, have the testbed be modular and extensible, and have it provide telemetry. So Elixir does all these things, but of course, there's still work to be done in all of them. And another goal of this consortium is to standardize benchmarking methodologies. So that includes applications, data sets, system configurations and metrics. And the last goal would be to help build the XR systems research community and have it come together, because right now there's a lot of XR research in the applications of XR, but not so much systems. And the systems research that is going on is very fragmented. So we were hoping this consortium could help bring that community together. And if you want any more information, you can visit the website at illixr.org. And I'll hand this off to Boyuan, who will talk about the specifics of the Elixir system.
Now I will give you an in-depth tour of Elixir. At a high level, Elixir has three interacting pipelines commonly present in any generic XR system. The perception pipeline determines how the world around a user looks and computes a pose to describe the user's position and orientation. The visual and audio pipeline then takes the pose to generate the pixels and the spatial audio from the user. The various components of these pipelines interact through the Elixir communication interface at the runtime. Elixir supports XR applications through an emerging interface named OpenXR, and we use an open source implementation called Monado. Right now, all of the components are in software designed to run on a mobile device, but we plan to include hardware acceleration in the future. Now let's look at each part in more detail. We begin with the perception pipeline, which interfaces to sensors like the camera and the IMU to provide the input to the system. We have the visual inertial odometry, or VIO, to provide the user's pose. VIO works at the camera frame rate, which is too slow to be the only pose producer. We therefore have the IMU integrator, which interfaces with the IMU and the VIO to provide a higher frequency pose. The next critical part is the pose predictor, which predicts the pose from the IMU integrator to future timestamps, and I will explain why we need it soon. Elixir supports scene reconstruction that builds a dense 3D map of the world, and we also provide eye tracking to determine where the user is looking. The Vero pipeline takes the user's pose to render a frame. However, the pose may change between the rendering start and finish, resulting in a temporal mismatch between actual and displayed motion, which is quantified by motion to photon latency. An efficient way to reduce the latency is to reproject the rendered image to the pose it will be displayed, which explains the job of asynchronous reprojection and why we need a pose predictor. Another feature we support is to track the distortion caused by the camera lens, which is integrated with reprojection. Finally, Elixir provides computational holography to deal with the fatigue caused by a single focal plane on today's display. It instead enables multiple focal planes by computing a per-pixel phase shift. The audio pipeline provides the 3D spatial audio that accounts for a user's pose. It first encodes multiple sound sources into a higher-order ambisonic sound field, which can be easily manipulated. Given the user's pose, it then plays back the encoded sound field after rotating and zooming computations. Elixir is not just a set of individual components, but a complete system with a runtime that orchestrates the system's data flow. Now let's take a look at how the system works. We begin with the IMU and the camera data. Both of them are fed into the VIO that runs at the same frequency as the camera. The IMU integrator then takes the VIO's result and IMU readings to generate a high frequency and accurate pose, which will be used later. Meanwhile, eye tracking and scene reconstruction provides the information about the user and the surroundings, which are consumed together by the application to render a frame, on which the reprojection and hologram computation will be operated. The audio information is recorded and gets played back using the user's pose data. So this diagram here shows a complex system with components running at different frequencies, multiple interacting pipelines, different dependency types, and multiple QoE metrics, calling a carefully designed runtime to handle all the aspects. The Elixir runtime is designed to be modular and flexible to enable various research and projects. The runtime orchestrates separately compiled and dynamically loaded components, making it easy to add new components and swap new implementations. The runtime is also efficient and provides a flexible communication interface in a way that each component is a specified event stream to publish and subscribe. Each component provides its synchronous or asynchronous consumers, and the runtime provides a copy-free implementation using shared memory. In summary, Elixir is an end-to-end system that balances flexibility with efficiency. Elixir also supports two ways of using XR applications, one directly written to Elixir, and the other through the OpenXR Monado interface. While Elixir supports the OpenXR compliant Godot game engine so far, other popular engines such as Unity and Unreal have started to support OpenXR, and we will support them soon. Elixir provides various end-to-end quality metrics. It reports the measurement to the motion to photon latency, which is critical to the user experience. It provides state-of-the-art metrics like SSIM and FLIP for evaluating image quality. It also has extensive telemetry such as frame rates, time distributions, power, and so on. More importantly, Elixir is extensible to many other metrics. Here we show the components and implementations supported by Elixir so far. It is continuously increasing as we speak, and we recommend checking more details in the paper. Next, I will pass this on to Yihan.
I will briefly explain our results from Elixir and their implications for system designers, architects, and other researchers. Elixir has an extremely large design space due to having multiple component choices and tunable knobs. With a lack of automated tools, we hand-tuned each parameter and selected one configuration that provides a good user experience. We listed the tuned parameter here, and all the results you will see will be collected using this particular configuration. Elixir has been tested on two platforms, a high-end desktop machine and an embedded platform with two different modes. We chose 4 AR/VR applications from the Godot game engine with varying graphic intensity. We have collected a variety of metrics, including frame rates, time per frame, and the distribution of cycles. We also collected power and power distribution and the quality of experience metrics such as motion to photon latency, SSIM, flip, average rotation, and precision errors. For more information about the measurement results, please read our paper. Next, I will quickly summarize the implication of these collected results. We first showed a substantial performance, power, and quality of experience gap, which motivates specialization throughout the stack, including hardware, software, and the entire system. We also showed no application components dominate all metrics, and we need to consider all application components in the system together. For example, VIO may be expensive on the performance, but the reprojection that uses VIO is important to reduce motion to photon latency. In addition, a system-level view of power is important. We showed that power consumption goes beyond CPU, GPU, and memory, where system-level components like display and I/O has also need to be taken into design consideration. Furthermore, we saw that a significant variability in the execution time of components, which motivates research questions in partitioning, resource allocation, and scheduling of system-level resources in an efficient manner. Lastly, we pointed out that looking at individual components in isolation does not often capture what the final system will do. There is a need to look at the entire system while making quality of experience-driven trade-offs. We also did a lot of analysis of individual components that make up Elixir. We looked at the microarchitecture behaviors and the task diversity of each component. There are several implications we can also draw based on per component results. First, given the abundance of tasks and no single task dominates, manually figuring out what to accelerate and designing that particular accelerator might not be feasible. This design difficulty motivates the need to develop automated techniques to determine what to accelerate. It might also be impractical to build a unique accelerator for every task. Therefore, we must reason about building shared hardware. The final SoC must provide flexible on-chip memory and communication interfaces to accommodate the varied compute and memory primitives found within the different components. And given that the components are still in flux and the algorithms are still being designed, a certain level of programmability will be required in the hardware. Finally, given that different algorithms have different trade-offs in terms of quality, power, and performance, we would require an end-to-end quality of experience-driven methodology for coming up with approximation techniques. In essence, future XR systems require application-driven, end-to-end quality-driven, hardware-software application co-designed system specialization, and Elixir is a perfect playground for performing XR system research. In fact, we have already started many ongoing work in our group along with our collaborators. Here is a list of ongoing works in academic research, Elixir testbed, and the Elixir consortium. To recap, Elixir, the Illinois Extended Reality Testbed, is the first open source testbed for extended reality that provides a rich space for XR system research. Elixir aims to democratize XR system research, development, and benchmarking. To learn more about Elixir, please read our paper, visit the elixir.org or contact us at elixir@cs.illinois.edu. Thank you.